Paper of the day is What Happens During a Join, Dissecting CPU and Memory Optimization Effects. Performance of modern hardware increasingly depends on proper utilization of both the memory cache hierarchy and parallel execution responsibilities in today's superscalar CPUs. Recent database research has demonstrated that database system performance severely suffers from poor utilization of these resources. In previous work, paper presented join algorithms that strongly accelerate large equijoins by tuning the memory access patterns to match the characteristics of the memory cache subsystems in the benchmark hardware. In order to make such algorithms applicable in database systems that run on a wide variety of platforms, paper now presents a calibration tool that automatically extracts the relevant parameters about the memory subsystem from any hardware. Exhaustive experiments with joint queries demonstrate how a database system equipped with these calibrators can automatically tune memory-conscious database algorithms to their optimal settings. Once memory is optimized, CPU resource usage becomes crucial for database performance. Paper demonstrates how CPU resource usage can be improved by using appropriate implementation techniques. Joint experiments with the modern database system on various hardware platforms confirms that combining CPU and memory optimization can lead to almost an order of magnitude performance improving on the modern processors. Here's a key figure from the paper which shows modern CPU memory computer architecture. As you can see, there's a L1 instruction cache, L1 data cache, TLB, and then from the L1 instruction cache we have fetch and decode units, which goes to instruction queue, and then that goes to execution units. And then on the top we have L2 cache lines, and then there's a system bus connecting L2 cache line to main memory and to disk drive. In the main memory you have memory pages, 4 KB each, and on the disk you have virtual memory and swap file. Let's see the approach the paper takes. So surgical instruments. To analyze the performance behavior of the algorithms presented in the paper, they break down the overall execution time into following major characteristics of costs. The first is memory access. In addition to memory access costs for data as described in the section 2.1 of the paper, this category also contains memory access costs caused by the instruction cache misses, CPU stalls. Beyond memory access, there are other events that make the CPU stall, like branch mispredictions or so-called resource-related stalls. Third is divisions. The paper treats integer divisions separately as they play a significant role in hash joins. Real CPU. This is the time the CPU is indeed busy executing the algorithms. Looking at the conclusion, the research presented in the paper shows that the results earlier obtained on one specific platform can be generalized to other hardware, and how cache-conscious query optimizations can be generalized and incorporated into existing DBMS technology. A key element for achieving this is the calibrator program they provide that automatically discovers the memory subsystem of the computer, what the memory subsystem of the computer looks like, and derives important cost model parameters like cache line size, number of cache lines, latencies. Combining the parameters derived from the calibrator on a number of new platforms, they additionally tested it on Sun, Intel, and AMD hardware with detailed main memory cost models provided in the section 5. They were able to successfully predict performance. Hence, they conclude that generic optimization of main memory access cost is both feasible and desirable, as correctly tuned cache-conscious algorithms greatly enhances DBMS performance. The paper gets 7 out of 10. The paper is well structured and provides a thorough examination of join operations, offering both theoretical insights and practical solutions.